us resume our conversation about the myelination process in an in vitro setup, how you can achieve. So, in the last class, remember I introduced the peripheral neurons and I allowed them to grow. So, let us pick it up from there. Week 6, lecture 3. Okay. Now, at this stage, you are introducing, I told you that allow them to grow 3-4 days, then you introduce the Schwann cells, which are smaller in size. So, once you allow the Schwann cells to get there, what are the possibilities? So, one thing which could happen is the Schwann cells will migrate towards the axon, and along the axon the Schwann cells may form exactly the way it happens. They may slowly divide like this, and they may form what I was trying to tell you is something like out here, something like this. Or this may not even ever happen. Okay? So, they go and close in there and they started forming the sheets like this. They go and wrap around it. This is one thing which could happen. Now, when I have said you, we could target the problem in a different way. Before I get into that, now think of it. So, once they are getting in, so they will have a finite, they have to, it has to be ensured that their division, because these cells will be dividing, it should be finite. If it is more than it, then it is going to outnumber. So, in the same culture model, you have to ensure that you have first a common medium allowing growth of both neuron and glial cells, in this case the Schwann cells. Okay. But then one has to ensure these cells which, in order to achieve its biological role of forming the myelination where it has to divide, this division has to be finite. Why it has to be finite? Because otherwise this is going to completely cover the dish. You won't be able to really figure it out. Okay. How one can do so? Then possibly at some point or other, in order to restrict the division, you may have to use something called an anti-mitotic. Anti-mitotic is something which prevents the mitosis to happen. Now, one has to be very, very careful, something like furacy, and there are several such compounds, cytosine arabinosidase, which is one of such compounds, which basically what the way they work is very simple. So, when the cell is dividing, say for example, this is one cell which is dividing. So, you must have seen that there are two levels of divisions which takes place. One is the nucleus divide and then the cytoplasm divides. But this division is being happening because of all those centrioles and all those formation of mitosis and all those things, you remember. So, cytosine arabinosidase ensure that they do not separate out, which is kind of a very ugly way of doing suppressing the cell division. but these are some of the very oldest techniques which are being used, but there are other techniques where you can deprive them from serum and other unknown factors. You can stop their division, but one has to do that division. Stopping that division is essential, but in a very controlled way, so that you can achieve your goal of seeing the myelination happening as well as seeing the nodes of Ranvier formation and their electrical properties. They regain it. So, we have not touched that point yet. So, now coming back, what is the other way you can look at it? Other way you can look at it is another interesting way, where many people have tried is, say for example, you form a bed of myelinating cells. On the bed of myelinating cells, you grow them. So, here what you did, the first case study when I said you put the peripheral neurons first, followed by Schwann cells second. You can reverse the order. You could have, if this is one paradigm you are following, there is another paradigm you can follow, where you put the Schwann cells first and you put the peripheral neurons second, or you could have a third paradigm where you put the Schwann cells and the peripheral neurons together. There are only three things you can do. So, if you break up the problem right, then in one of the three experiment, of course, your luck has to be on your side and your hard work also, you will be able to achieve the problem. The second situation is that you put the Schwann cells first out here, and top of that you start putting the neurons, assuming that as the neuron will be sending out its processes, these Schwann cells will come along and form the wrapping. Or you have a third situation, which is out here, you put them together. So, at this stage, I will give you the papers, what has been achieved. I will not really divulge that, I will leave it to your judgment, how we did it. But what is important is part 2 of the paper, what I am going to discuss with you, but we went through the whole rigor. The whole idea about telling you these stories from real time is, this is how you have to understand cell culture. The modern day cell culture is no more like, add this, add that and something happened. No, you have to think rationally. Our body has formed in a systematic way, component 1, component 2, component 3, component 4, and slowly it has built it itself. And now what you are trying to do is, you wanted to see an in vitro development outside the system. That is not an easy job. It is something exceptionally challenging. And how you can achieve it? It will be a long drawn process. It will be a long haul journey of ours to understand even, going even close to it. But it all starts with that simple modesty of doing these experiments right. So, this is the way we thought it out. I still remember that what are the possibilities? This is one possibility, this is the second possibility, this is the third possibility. And we tinker around it on a dish that which one is going to work. Okay? So, these are some of the stuff which I want you guys to think, but then what one has to achieve. Okay. Now, here is the interesting part, one has to achieve. So, now if you look at the neurons when they are forming a myelination. So, this is the classic part, what you will be observing. These are the dendrites, and assume that this is where you are seeing the myelination. Right. So, now this zone, which we call as nodes of Ranvier, this particular spot is very rich in sodium channels. Right. So, now when you achieve, if you believe you have achieved it, first thing you have to see whether you could make or form a nodes of Ranvier or not. So, you have to stain these cells in a culture before you claim that you have done it, is with myelin basic protein. We have talked about it, the antibody against myelin basic protein. You have to identify the nodes of Ranvier by specific sodium channel antibodies against sodium channel, and at this nodes of Ranvier there are different nodal proteins you have to develop, or you have to get the antibodies against them to make a claim that you have achieved this. And on top of that, you have to have electrical recording from these neurons, and you have to measure the conduction velocity, and you have to compare the conduction velocity of these neurons along with a neuron without myelination. Comparing conduction velocity between non-myelinating versus myelinating neurons. Then only you will be able to make a claim of whether you have achieved it or not. Now, we try to see that how a trivia problem called cell culture can become so very interesting and so very fascinating to appreciate that the possibilities, the window of possibilities is unparalleled. There are so many beautiful things you can achieve in a dish, and that will give you a joy to see this is how the life is formed. So, now having said this, this is one part of the problem where we started. Let us go back and let us don't lose track of it, because I have digressed a bit. So, this is where we all started, right. So, this was the problem which I am supposed to target, but I think I will be able to target this problem. It will take me another couple of more classes before I kind of hit upon that problem. Now, having said this, where we started. So, now you have a fairly good idea how to have a cell culture model for peripheral neurons. Now, how to achieve for central nervous system neurons? We have not talked about it yet, right. Now, let us break the problem. Now, I will come here if I have to break the problem. So, you will be needing oligodendrocytes if you want to achieve a myelination, and you will be needing adult neurons. So, just like this problem, in the peripheral nervous system we use the embryonic system in order to achieve it before we graduate into adult. And to the best of my knowledge, as of now, there are hardly any groups in the world which has achieved myelination on adult neurons. Not that I know of, but any one of you find it out in a culture dish, people have achieved. That would be a really great thing, but it is exceptionally challenging. But here also we will talk about the myelination problem with respect to the cell culture context, with respect to embryonic neuron, because these are some of the models which has been successfully demonstrated that it is possible. As of now, technologically it is, so mark my word, it is technologically very challenging to target the second level of problem, where you will be using the adult neuron to get myelinated. Okay. So, now in terms of the oligodendrocyte myelination. So, here I told you the way the myelination is happening, these cells are coming close and eventually losing their identity and secreting myelin basic protein, which is this one, and this is how the myelination coverage is happening. And then you have the nodes of Ranvier, where you have a significant population of sodium channels which are labeling. But in the case of central nervous system, if you want to achieve it, this does not work like that. In the central nervous system, the myelination is carried out by oligodendrocyte, and the way oligodendrocyte works is that oligodendrocyte cells they resemble something like this. Initially they look like this, and then they send out processes like this, multiple processes on multiple directions, very multipolar cells. And these multipolar cells, after coming in contact with any axon, they form something like this. That is after coming there, and this is the part where they secrete the myelination protein. So, if there is another oligo coming from the other direction, so it will form a sandwich. Just imagine in between there is a process going on, and from here something like this, and the another direction something like this. Okay. Slowly, using multiple oligodendrocytes, it will myelinate the central nervous system neuron. So, central nervous system neuron their processes does not become as thick as the peripheral nervous system neuron, where you have a thick coating and covering, because central nervous system has a limited space to expand. It cannot expand beyond it. So, now in order to achieve it, if you really want to achieve, your first target is you needed to have a source of neuron. Now, again let us break up the problem in terms of the way we break it up here. Now, achieving myelination, now I am just changing, okay, peripheral, now I make it central nervous system. Okay. This is central nervous system, then its corresponding myelination disorder, of course, that remains the same. In order to achieve, now instead of Schwann cells, this will become oligodendrocytes. So, central nervous system and oligodendrocyte, and the problem is achieving myelination. Of course, for neuronal source central nervous system, you are using embryonic tissue, which depending on what kind of cells you want to achieve, for what kind of cells, if you are using oligos, then of course your best bet will be hippocampal neurons, which I have already talked to you. So, you have hippocampal neurons, which are basically the pyramidal neurons of embryonic origin, and you wanted them to get myelinated with oligodendrocytes. So, what is important here for you is to understand the kind of problems what the modern cell culture will be dealt. These are the kind of problem one has to appreciate, and what level, which kind of tissue you are using, it does not matter. I am taking this study in terms of the nervous system, because this is that is the most fastidious one, but you can translate it with any other tissue, whether it is a pancreatic tissue, liver tissue, kidney, whatever, it does not matter. What it matters is how you target the problem. That is the most critically important things. And in a modern day, if you really want to make a difference, then you have to have a proper paradigm to achieve this. How you are going to do it in terms of paradigm, this is what I am talking about, that who will come first, what will be the paradigm. This paradigm has to be defined, step 1. Second, you need a defined protocol so that everybody can follow. Then you have to have a defined medium, then you have to have a defined surface. And once you can pull all this together, you really can contribute in a big way in developing defining systems to achieve these kind of problems. Okay. So, with this background, with this aspect, I will close in this lecture, and I will send the handouts which will help you to appreciate these kind of problems and how these could be targeted. There are whole sorts of protocols which are involved in it, but the important part is to understand the philosophy of targeting this kind of problem and how we can make a difference in the drug discovery process. Thank you.